Okay, so we're on to the two-body momentum problem. So let's do this. As usual, it's page 20 of the notes, unit 6, conservation of momentum. As usual, we check out our givens. 1,000 kilogram cannon, 50 kilogram cannonball. So we got our here mass of the cannon, mass of the cannonball. You got two masses in here. Differentiate via subscripts. C for cannon, B for ball. You could have 1 and 2, but something. At a velocity of 90 meters per second, west! Let's declare west positive. We're dealing with velocities, vectors, momentum, vectors, so keep track of your direction. So, what's traveling at that velocity? Fires a 50 kilogram cannonball at a velocity. So it's the velocity of the ball. We define west to be positive, so we can leave that 90 meters per second. Determine the recoil velocity of the cannon. Now, from these givens alone, how do you know what to do? Well, masses and velocities should get you thinking about momentum. So maybe something with momentum. We have two objects. We have an explosion. In particular, it's a cannon firing a cannonball. We have the word recoil. All of those are signals that this is a conservation of momentum problem. And so what I strongly recommend you do is break your problem into before and after. Before and after what? Before and after the explosion or the firing of the cannon. So before the cannon, we have a total momentum. In your reference table it says P before equals the total momentum after. Good. Next, before the explosion, our momentum is contained in two objects, the cannon and the cannonball. So, you have the momentum of the cannon before the explosion, plus the momentum of the cannonball before the explosion. That total has to equal the momentum of the cannon after the explosion, plus the momentum of the ball, that combination, after the explosion. So far all we've done is rewritten what was already in our reference table, P before equals P after. Now this is nice, but if you notice our givens are masses and velocities, so make these look like masses and velocities. Momentum equals mass times velocity, so we can actually rewrite each term here. Momentum of the cannon before is the same thing as the mass of the cannon times the velocity of the cannon before it explodes, plus the mass of the ball times the velocity of the ball before it explodes, and that must equal the mass of the cannon times the velocity of the cannon after the explosion, plus the mass of the ball times the velocity of the ball after the explosion. Now it's a mouthful to say all this together. Really, you have to be disciplined about setting up your conservation of momentum. Make sure you are separating before and after, and make sure you're separating by the objects. So an explosion is actually a fairly simple mathematical problem to run through. Here's why. Before it explodes, the cannon has a mass of 1,000 kilograms and has a velocity of, and this is where the before comes in, before it explodes, you have the cannon and the cannonball. It has not yet exploded, it's just sitting, waiting. How much velocity do we have here? None! So, before the explosion, we have velocity of 0. Plus, the mass of the ball is 50 kilograms times its velocity before, which is also 0. Be careful, that 90 is after it's exploded. We're on the before side. Both these are 0, you can hash them out right away. This whole side is where it's 0. That 0 matters though. Don't write nothing, you have to write 0. Equals, because we have equality here and we still have to do algebra. The mass of the cannon, still 1,000 kilograms, times its velocity after, well, we don't know what that is, that's actually the question, plus the mass of the ball, 50 kilograms, times its velocity after, which we know to be 90 meters per second. Okay, so now it's just a basic algebra problem. So, just be careful with what you do. 0 equals 1,000 times velocity of the cannon after, plus 5 times 9 is 45, 10, that's 4,500. Subtract 4,500 from both sides. This is why we needed that 0 over here to remind us to do this. That comes out to nothing. Negative 4,500 equals 1,000 VC. To finish the problem, divide both sides by 1,000. and your velocity of the cannon after will be negative 4.5 meters per second. Now, since we defined positive to be west, this is also written as 4.5 meters per second east. One or the other. Don't write the negative and east. It's either negative or east. There's your answer. Good. Now we come down to this next one. Here, we have a garbage truck. They give its mass. Okay, so the mass of the truck, 8 times 10 to the 3rd kilograms. Traveling at 12 meters per second south. Let's call that positive. So the velocity of the truck is 12 meters per second. Rear ends a 2,000 kilogram Corvette. Mass of the Corvette, 2 times 10 to the 3rd kilograms. That is stopped at a red light. Also, the initial velocity of the Corvette is 0. And this actually is an initial velocity too. You realize it's coming to rear end this Corvette. The item of interest is the collision. This is before the collision has happened. After the collision, the garbage truck, so the velocity final of the truck is 6 meters per second, still south, so positive 6 meters per second. Determine the velocity final of the Corvette. Okay, well let's see. The word collision, masses and velocities, the actual car hitting car. This sounds like conservation of momentum problem, and it is. Before equals after. And so, you can break this down just like the reference table. P before equals P after, and then start running your numbers. Now, you may realize, oh, well, it's just the truck and the Corvette, and so I'll do the complete. Momentum of the truck before plus the momentum of the Corvette before is the momentum of the truck after plus the momentum of the Corvette after. Some of you may even jump directly to the mass velocity line. Just be careful. If you do that, it's okay, but sometimes they'll actually give you a momentum, just to keep you honest, where you would plug it in on this line. So mass of the truck, velocity of the truck before, plus the mass of the vet times the velocity of the Corvette before, must equal the mass of the truck, velocity of the truck after, plus the mass of the Corvette, velocity of the Corvette after. Keep saying that before and after in your head. Keeps you honest with these. All right, let's plug them in. At this point, the math is usually pretty straightforward. Just be careful. The truck is 8,000 kilograms. Its velocity before was 12 meters per second. Corvette is 2,000 kilograms. Its velocity before it was at rest is 0. You can get rid of that immediately. The truck after is still 8,000 kilograms. We assume it remains intact. We actually are trying to, oh no, we do know its velocity after. It's 6. Plus the mass of the Corvette after, still 2,000. And that's the velocity we're trying to find, the velocity of the Corvette after. So run our numbers. 8 times 12 is 96. So you have 96,000 kilogram meters per second. Is 8 times 4 is 48,000 plus 2,000 velocity Corvette. Alright, so should be good to go. Subtract 48,000 from both sides. Remember, we're trying to solve for VC, so get everything else away from it. Isolate it. Start far away and then move in. So first we'll get rid of this 48,000, left with 48,000 equals 2,000 VC. Divide both sides. Divide both sides. 0, 0, 0. 2 into 48 is 24. The velocity of the Corvette is 24 meters per second. Since it's positive and we call it south positive, this actually would still be south. Good. 24 meters per second south. So, let's go to the next one.